How SSDs store 8 terabytes of data. What if I told you that 8 terabytes of storage could now fit inside something smaller than your phone? It sounds almost magical, like science fiction, but it's not. It's the real-world power of modern solid-state drives. These drives are silent, lightning-fast, and compact beyond belief, yet inside that sleek little shell lies a technological wonder built from decades of innovation. How do they work? How can something so small hold a library of digital information larger than most people will ever need? Today, we're cracking open the black box, literally and metaphorically.
We'll step into the microscopic world where electrons are trapped, layered, and manipulated to store trillions of bits. This is the story of how SSDs manage to pack thousands of gigabytes into a space smaller than a matchbox.
Using quantum physics, stacked architectures, multi-level logic, and some of the most sophisticated control systems in consumer electronics. Ready to dive in? Chapter 1. NAND Flash Memory. At the very heart of every solid-state drive is a small but powerful technology called NAND flash memory. It's the foundational material that makes the magic of SSDs possible. Unlike traditional hard drives that use spinning platters and mechanical arms, SSDs rely on NAND flash to store data electronically.
But what makes NAND truly special is that it's non-volatile, meaning it can retain information even after the power is turned off.
The magic happens inside something known as a floating gate transistor. Each memory cell in a NAND chip stores data by trapping or releasing electrons in this gate. When electrons are trapped, the cell is considered to be in one state, let's say a 0. When electrons are absent, it's in another state, 1. This binary system, the backbone of all digital technology, is made possible by a phenomenon called quantum tunneling, where electrons pass through insulating barriers at the quantum level to move in and out of the gate. Billions of these tiny cells are organized into arrays. Just imagine a microscopic city where each building is a memory cell capable of holding a bit of information. The scale is mind-blowing. Is the precision required? Even more so. This is the level at which SSDs operate, reliably storing your documents, photos, games, and operating system on a sea of trapped electrons. Chapter 2. Scaling with 3D NAND. As technology evolved, we hit a wall with traditional, flat NAND memory. We simply couldn't cram more data onto the same 2D plane without interference and performance degradation. The solution? Go vertical. Enter 3D NAND, a revolutionary shift in memory design. Instead of laying out memory cells side by side like houses on a street, engineers began stacking them vertically like floors in a skyscraper. The result is astonishing. Some of today's chips boast over 170 stacked layers, each filled with dense arrays of memory cells.
This vertical stacking isn't just about saving space. It unlocks massive storage potential. By stacking cells,
We can fit exponentially more memory in the same footprint. It's the same principle that makes skyscrapers ideal in crowded cities: more capacity without expanding the footprint. Of course, building in 3 dimensions on a microscopic scale is an engineering nightmare. These structures are built using advanced etching and deposition techniques at the nanometer level. Precision is critical. The layers must be perfectly aligned, insulated, and electrically connected. If even a few layers malfunction, the integrity of the entire chip could be compromised. But when done right, the result is transformative. 3D NAND allows us to create storage chips capable of holding terabytes of data, all while reducing cost per gigabyte and improving power efficiency. Chapter 3. Multi-level cells MLC, TLC, QLC. Now that we've stacked memory vertically, the next challenge is to store more information in each cell. In the early days, each NAND cell could hold only 1 bit, either a 0 or a 1. This was called single-level cell SLC memory. It was fast and durable, but not space-efficient.
engineers quickly realized they could do more with the same space.
By using different voltage levels to represent more than 2 states, they could store multiple bits in a single cell. 2 bits per cell became a multi-level cell MLC. 3 bits? That's triple-level cell TLC. And now we have a quad-level cell QLC, storing 4 bits per cell. It might sound simple, but the reality is incredibly complex. Each extra bit exponentially increases the number of voltage thresholds that must be distinguished. For QLC, the cell must reliably detect one of 16 different voltage levels. That's like trying to tune into 16 radio stations using a dial the size of a grain of sand. Chapter 4. The SSD controller. Inside every SSD is a microprocessor known as the controller. If NAND flash is the body of the SSD, the controller is its brain. It's responsible for translating the chaos of modern data usage into order. Think of it this way: when your computer saves a file, it doesn't write it in one neat block. It's broken up, spread out, moved around. The SSD controller decides where each piece goes. It tracks every byte, handles background tasks, and ensures that performance remains smooth even under load. But its job doesn't stop there. The controller also performs wear leveling, spreading out writes evenly across all cells to prevent any one area from wearing out too quickly. It handles error correction, detecting and fixing mistakes on the fly. It runs trim operations, cleaning up deleted data so the drive stays snappy. Some even encrypt your data in real time. Modern controllers are marvels in their own right, equipped with multiple cores, DRAM caches, and even machine learning algorithms to predict usage patterns. Without a good controller, even the best NAND is useless. It's the conductor of a very delicate orchestra, keeping every part in harmony. Chapter 5. Endurance and data protection. If there's one downside to NAND flash, it's that it wears out. Each write-erase cycle physically degrades the cell's ability to trap electrons. Over time, the cell becomes unreliable. That's why SSDs don't last forever. But thanks to clever engineering, they last a lot longer than you might think. Error correction codes, ECC, are always watching in the background, identifying and fixing small errors before they become big ones. Over-provisioning means extra memory is set aside, invisible to the user, to replace bad blocks when they fail. It's like having a spare tire for your data.
Put it all together, and you get a device that's both high performance and surprisingly durable, capable of writing hundreds of terabytes before showing signs of wear.
Chapter 6. NVMe versus SATA. If you've ever compared SSDs, you've probably seen two main types, SATA and NVMe. While both use NAND flash, their interfaces couldn't be more different. SATA was designed for hard drives. It's a legacy interface capped at around 550 megabytes per second due to its limitations. For years, it was fine, until NAND got fast. Suddenly, the bottleneck wasn't the memory, it was the interface. That's where NVMe comes in. It connects directly to your motherboard's PCIe lanes, allowing for data transfer speeds that exceed 7,000 megabytes per second in modern Gen 4 and Gen 5 models. That's not just a small boost, it's a leap. The difference is dramatic. Imagine switching from a dirt road to an 8-lane superhighway. File transfers become nearly instant, boot times shrink to seconds. Applications launch with zero hesitation. NVMe SSDs also tend to come with DRAM cache and more powerful controllers, further enhancing their capabilities. It's the reason high-end desktops, gaming rigs, and even modern laptops prioritize NVMe drives. They unlock the full potential of NAND flash. Chapter 7. How we fit 8 terabytes on a chip. So how do we pull it all together? How do we take all this science, all this engineering, and make something the size of a postage stamp that can hold 8,000 gigabytes of data? The answer is elegant and layered, literally. We start with 3D NAND stacking over 170 layers of memory cells vertically. Then we use QLC technology, squeezing 4 bits into every single cell. That gives us an incredible amount of raw density. Next, we add a high-performance controller, capable of managing the chaos, correcting errors, and keeping everything running smoothly. Behind the scenes, techniques like wear leveling, ECC, and TRIM are hard at work protecting your data. Then we put it all together on an NVMe interface, letting data move at breakneck speeds. And finally, all of it is housed in a chip smaller than your thumb, ready to sit inside your laptop, your PS5, or even a portable SSD drive you toss in your bag. If this deep dive into SSDs blew your mind even a little, why not hit that like button? Maybe subscribe if you're hungry for more tech breakdowns like this.
We're just scratching the surface of what modern hardware can do. Thanks for sticking around. Stay curious, and I'll see you in the next one.